So I was organizing thousands of files recently. You know how it is, just a total nightmare.
Oh, I know that feeling.
And it got me thinking.
Hmm.
When we intuitively look for that one PDS saved deep inside, like 5 nested folders, we're just using instinct.
Right.
But a computer, for it to guarantee it finds every single piece of data in that hierarchy, it needs formal, precise rules.
And that's the mission of this deep dive. We're getting into tree traversal algorithms, or what's often called walking the tree.
Walking the tree. I like that.
It's a good way to picture it. And unlike just a simple list, a tree structure forces you to choose an order. You have to commit to one of two fundamental strategies to make sure you visit every single node just once.
Depth first search, DFS, or breadth first search, BFS.
Exactly. And that choice between depth and breadth, well, it determines everything.
Okay, so let's unpack depth first search first. As the name implies, DFS means you plunge down a path as far as you can possibly go.
All the way to the end of a branch. Yep. Before you backtrack and then move over to the next sibling branch.
What's really fascinating, though, is a DFS isn't just one thing. It's more of a family of methods, right?
That's a great way to put it. For binary trees, there are 3 really elegant methods, and they're all defined by the sequence of visiting the node, which we'll call N, the left subtree L, and the right subtree R.
So first you have preorder. That would be NLR, node left, right. You visit the parent node first.
Correct. This gives you a kind of topological sort where you're guaranteed to process the parent before any of its children.
And what's that good for?
It's perfect for making a faithful copy of the tree structure. It's also used to generate something called a prefix expression.
Polish notation.
You got it. And that matters because it helps simplify computation. For a compiler, that order removes any ambiguity from equations, without needing parentheses.
Okay, and the second one is inorder, LLNR. So the parent node gets visited between the left and right traversals.
And if you're working with a binary search tree, in order is, it's just crucial. It's basically a zero-cost sorting mechanism. It retrieves every key in perfect ascending sorted order just by walking the structure. It's pure algorithmic elegance.
And the last one is postorder, LRRN. The node is visited last after its children.
Postorder is like the cleanup crew. It's what you'd use to safely delete a tree because you have to free the memory of the children before the parent.
Oh, that makes sense.
And just as importantly, it generates the postfix representation or reverse Polish notation. RPN is vital for stack machines because, like the prefix version, it makes complex calculations much simpler for a computer to execute. So if DFS is all about going deep, breadth first search, or BFS, is about going wide.
Level order search?
Exactly. You process all the nodes at one level before you ever go down to the next one. It's a completely different philosophy.
And where do we see BFS in the real world?
It's everywhere you need efficiency. BFS is the go-to for finding the shortest path between 2 nodes in a graph that isn't weighted.
So your GPS finding the route with the fewest turns.
That's a perfect example. Or how a social media site maps the connections between you and someone else with the smallest degree of separation.
So if we think about the implementation, DFS is kind of like handling the most recent box you touched, last in, first out.
Right, which is why it's so naturally implemented with a stack. Often it's just the implicit recursive call stack.
But BFS is different. It's like waiting in line, first in, first out.
Precisely. And for that, you absolutely require a formal queue to keep track of the nodes and make sure you process them strictly level by level.
You know, this ability to structurally solve these organization problems is just so fundamental to modern computing.
It really is.
And if you're looking to uncover where cutting-edge AI agents could make the most impact for your business, from automation to complex data analysis, you should check out embersilk.com. Embersilk can help you integrate and optimize these very data structures and systems for the AI age.
And if we connect this back to the big picture, these principles, they guide so much more than just file navigation. They're essential when you're exploring these huge abstract structures.
Like the game trees for chess or Go.
Exactly. Those represent practically infinite decision spaces.
But simple algorithms must run into trouble on truly infinite structures, right?
Yep.
DFS would get stuck going down an infinitely deep tree.
It would. And BFS could get stuck on a level that's infinitely wide. But that's where human ingenuity comes in. We've developed hybrid methods, some that leverage a diagonal argument, which combines depth and breadth.
To make sure every node is eventually visited.
Guaranteed. It's just a testament to our ability to structure and, well, conquer information, even at an infinite scale. It really makes you think. When you look at any complex digital system today, your navigation app and AI exploring possibilities, just remember that its speed, its order, it all relies on a simple choice. Go deep or go wide.
These small, elegant algorithmic choices are really the quiet engine of all modern digital progress.
They absolutely are.
If you enjoy this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.